Now summations and the product. Suppose we have a sequence let A1, A2 be a sequence. Okay, suppose we want to compute the sum of some of the terms. For example, suppose I want to compute what is A1 plus A2 plus A3 and so on all the way to AN. So if every time I want to compute the sum, because for sequences, it's very common that we want to compute the summation. If every time I want to compute the sum, I have to write in this way, it's not very convenient. It's a cumbersome. So we need a very clean clean notation for this. For this purpose, people define this summation sigma notation. Use the capital Greek letter sigma, which stands for S. Just use sigma, and the lower you put the lower here, you use K as the index of summation. K is called index of summation. Okay, K equals 1 to N AK. Okay, and this 1 is called the lower limit. Lower limit. And N is called upper limit. So summation AK, K equals 1 to N. This is the way we are going to read the summation like this. That means K is the index of summation, and sometimes it's also called a running index. So basically, this is saying that I'm doing a summation. When you see the sigma, that means we are doing summation. And here, if you because K not only appear here but also appear in the summation notation here, that means K is the index of summation, and therefore, and the lower limit is K equals 1 from K equals 1 to N. That means I'm going to do A1, A2, and AN plus AN. Okay, let's see another example. Let's suppose I have S2 is equals to A11 plus A12 plus A13 all the way to A100. How are we going to express this using a sigma notation? So we can write sigma. For example, I change the index summation. I don't like K. I use I. That's also fine. You can use anything AI. But here is very important. You have to make sure the index summation is consistent. So I'm using I equals 11 to 100. Okay. And the next example, maybe I want to compute S3 equals A1 plus A3 plus A5 plus all the way to A2N plus 1. And how are we going to express such a summation? You can say AJ, summation AJ. What is the range of J? J equals 2. I'm sorry. Here, if you write AJ, it's not very good, because then you have to say J equals 2 minus 1, j equals 1, 3, 5, and 2 and plus 1. So instead of using 2j and aj, the better way is to write I want to make 2j plus 1. Okay. Now if I'm summing over a sub 2j plus 1, then I only need to run j from 1 to n. Okay, so you plug j equals 1, I'm sorry, j equals 0. So something wrong. J equals 0. Because when you plug j equals 0, you get a1. You plug in j equals 1, you get a3. You plug in j equals 2, you get a5, and so on. Finally, you plug j equals n, you get a2n plus 1. Okay, this is for summation. And for product, if I have a p, I define p equals a times a1 times a2 times a3 times an. And similarly, it's not as commonly used, I mean, because product is not commonly used as summation. We are going to use pi. Pi stands for product, the capital pi. So I'm going to write pi. Pi denote product. Okay, and this very similar to this summation. I have pi ai. I runs from 1 to n. This is the same thing as a1 times a2 times a3 all the way to an. Let me mention, give you a reason why you don't see product as often as summation, because product can be easily turned into summation. Why? Because you can take the logarithm of this p. What do you get? And you are going to get a log of a1 plus log of a2 plus log of an. And therefore, basically, you can turn this product into a summation. Okay, let's move on to the next page. So let me give an example of the summation. The first example is, I don't know if you heard about this before. I will call it Little Gauss. It's a very famous story of the great mathematician Carl Gauss. I think when he was in his when he was in middle school, primary school, he was asked to compute the following sum: s equals 1 plus 2 plus 3 plus 100. Okay, if we want to use the sigma summation, sigma notation, what we are going to get is summation k equals 1 to 100. And also, if you prefer letter I, that's also okay. I equals 1 to 100. J equals 1 to 100, summation j. It doesn't matter. Okay, the next example is we defined a sequence only in one variable, but you can imagine that we can have a two-dimensional sequence. Or we can define, you can think about this as aij. or if you're not comfortable with aij, you can think about a function defined fij. So basically the picture look like this. This is 1, 2, 3, 4, and so on. Suppose I want to do the summation fij. So this is called double summation. I equals 1 to n, j equals 1 to n. This is called a double summation. So what does this mean? For example, if n equals 4, that means I'm going to have f11 is going to be s11 plus f12 plus f13 plus f14 plus f21 plus f22 plus f23 plus f24 and so on. Okay, f41, 42, f43 plus f44. So basically, you are summing. You're doing a summation of 16 terms. So we can write this. And what about? Let me check your understanding of this. What if I'm doing summation like this? Fij. J equals 1 to I equals 1 to n. So what the meaning of this? So that means for fixed I, I'm summing over j equals 1 to I. So let's write this. Suppose n equals 4. What we are going to have? So we are going to have, let's say I equals 1. I'm going to have 1 1 f11. Just one term because j equals 1 to 1 to 1. So I equals 2. I'm going to have plus f21 plus f22. And I equals 3, I'm going to have f31, f32 plus f33. And finally, I equals 4, I'm going to have f41 plus f42 plus f43 plus f44. So what this doing? This is doing just we are summing over all the point, all the lattice point below this line of I equals j. That means we are summing over the lattice point in this region. Okay, let's move to the next slide. Let's do some example of summation. How do we do summations? In general, we don't have a general recipe of doing summations. So we have to work case by case. example of. So the first example we are going to do is the arithmetic progression. So suppose that Sn equals A plus D. This is the second term. So we have recorded for the arithmetic progression AK equals A plus K minus 1, sorry, KD, let's say KD. K equals 0, 1, 2, up to n minus 1. So you have n terms. So right in the, using the sigma notation, we have K equals 0, summing over K equals 0 to n minus 1, A plus KD. Okay, how do I do this? We can use Gauss's trick because remember Gauss's trick is like this. When you do the summation over 1, 2, 1 plus 2 plus 3, all the way to 100, your S is this. And then you rewrite S backward. So 100 plus 99 plus 98 and so on, and plus 1. And then you look at this these two summations. You see that the first term in the first summation plus the first term in the second summation, this, when you add these two, you get 101. You add this two, you get another 101. And from add this two, you get another 101. So you always get 101. And how many terms do you have? You have 100 terms. So the total is 100 times 101. But now you are doing 2s. 2s equals this. Therefore, s equals 100 times 101 divided by 2, which is 5,050. We can use the same trick. Sn equals A plus D plus A plus 2D and so on. Right, the last term is A plus n minus 1D. And we write S again, but in backward order. We have A plus n minus 1D plus A plus n minus 2D, A plus n minus 3D, and so on. And we add this to S again together. And the first term, we get 2A plus, sorry, the first term is here, 2A plus n minus 1D. And if we add the second term in the first summation with the second term in the second summation, we get another 2A plus n minus 1d again, like here, and like here, 2a plus n minus 1d. And therefore, what we get is 2Sn equals 2a plus n minus 1 d. How many terms do we have? We have n terms. And therefore, Sn is just Na plus n times n minus 1 divided by 2 times d. Okay, maybe that you find that this such a formula is not easy to memorize, but I will tell you a way of memorizing this, and so that also you understand. I will call this trapezoid method, because for arithmetic progression, the term look like this. This is A1, this is A2, and then you have AN. So it's just like a trapezoid. So the sum of this is just the first term plus the last term. Okay, if you recall, how do we compute the volume, the area of our trapezoid is the lower base plus the upper base and times the height divided by 2. And the same thing here, the height, the first term plus last term times number of terms divided by 2, which is first term plus last term divided by 2 times number of terms. And which, by the way, is also the way Gauss solved the problem. Okay, I'm going to show you another way of doing this. I call this probably this method is called the difference method, because we are going to see that this method, the second method, can be used to compute the summation of like this k square. K equals 1. To n, like 1 plus 4 plus 9. So what this? So we are going to use the second method to compute this. Keep this in mind. And also, I'm going to ask you to do this generalized to a sum of cubes. So the second method is it's a little bit tricky. So we notice that n minus 1 squared, the difference between n squared and n minus 1 squared, what is this difference? Because we know that n minus 1 squared is just n squared minus 2n plus 1. So the difference is 2n minus 1. Okay, so this is identity. N squared minus n minus 1 squared equals 2n minus 1. Okay. The trick is we rewrite this and decrease argument. We write n minus 1 squared minus n minus 2 squared. And so what we get is we just change the value from here. We just change to, we know the 2n minus 1, right? So now we change the value, the argument is changed from n to n minus 1, so it should be 2 times n minus 1 minus 1. Okay. So why we are writing this? Because if you look at these two equation, if we sum them together, we are going to have n squared minus n minus 2 squared equals 2n minus 1 plus 2 times n minus 1 minus 1. So we get rid of n minus 1 square in the middle. Okay, and this, so let's write another term you're going to see even clearer. So n minus 2 squared minus n minus 3 squared equals 2 times n minus 2 minus 1, and so on and so forth. So finally, we have 1 squared minus 0 squared equals 2 times 1 minus 1. Okay, so now if we add this all this equation together, what we are going to get? Because we have minus n squared, n minus 1 squared, and plus n minus 1 squared, they cancel. So this is phenomena is called telescoping. Okay, so we have n minus 2 squared, minus n minus 2 squared, and plus n minus 2 squared, they cancel. And so what we are going to end up with for the left-hand side, we just have n squared. And what do we get on the right-hand side? We just get, because in the first equation is 2n minus 1. Second is 2 times n minus 1 minus 1. Second, the next one is 2 times n minus 2 minus 1. So what we get is 2 times summation I equals 1 to n I. And then we have I equals 1 to n. But this one we know how to do it, right? Summation 1, summation I equals 1 to n. This is just count how many terms do we have. This is n. But this one is this term right here. This term right here is exactly what we want to compute, the sum. So we have n squared minus n. We just move this to this side, equals 2 times Sn. Sorry, should be n squared plus n, because this is minus. Move to this side should be and Sn summation I equals 1 to n, I equals n times n plus 1 divided by 2. This trick is very, very important. Let me show you the power of such a trick. Because if you use Gauss method, you won't be able to compute. Let me move to next page. You won't be able to compute the sum of this. Suppose my Sn equals 1 squared plus 2 squared plus 3 squared plus n squared. Using our sigma notation, k equals 1 to n k squared. So we're using the same trick, but this time we need to go to a higher polynomial. So we just make, if you don't know this identity, what is n minus 1 cube? This one is n cube minus 3 times n squared plus 3n minus 1. Okay, now we write n cube minus n minus 1 cube. What do we get is 3 times n squared minus 3n plus 1. And we write this again, n minus 1 cube, but change the the argument, decrease the argument by 1, n minus 1 cube minus n minus 2 cube. We get 3 times n minus 1 squared minus 3n minus 1 plus 1, and so on and so forth. So last term is 1 cube minus 0 to the cube equals 3 times 1 minus 3 times, 1 squared times 3 times 1 plus 1. Okay, now we sum them together. We are going to cancel this, cancel this, cancel that. So we are left with n cube on the left-hand side. And on the right-hand side, we have summation k equals 1 to n squared, k squared. Okay, 3 times k equals 1 to n, k squared. By the way, we want to highlight this exactly what we want to compute. And we have some other term, 3 times k equals 1 to n summation over k. But this one, we know how to do it. We already know from our previous calculation. And this, by the way, this is another example giving you, telling you how to do this summation using recurrence. Basically, if you know how to, what is this summation over k equals 1 to n k squared, you know how to do the k cube. Once you have k cube, summing over k cube, you know how to do k to the fourth. Once you have k to the fourth, not only k to the fourth, but you know summation over k, summation k squared, k cube, k fourth. You know how to do. You are going to have. You know you are going to be able to do the summation of k to the fifth. Okay, plus summation 1, k equals 1 to n. And this is nothing but n, but this time, this one is n times n plus 1. Divided by 2, this summation. And therefore, what we have here is 3 times Sn equals n cubed plus 3 times n plus 1 divided by 2 and minus n. And after simplifying, you are going to get this one give you n cubed, n times n plus 1 times 2n plus 1 divided by 6. It's very important you memorize this formula if you can. Okay, let's move to next one. And this is also the last example we are going to see. This is geometric progression. How do I do geometric progression? Actually, geometric progression, if you recall, is Sn defined a plus a times r plus a times r squared, and so on, a times r minus 1, r to the n minus 1. We are going to use this, a similar trick, but this time it's a little bit different. We multiply r we multiply the sum Sn by r times Sn. What do we get? Excuse me. We're going to have a times r plus a times r squared plus a times r cubed, and so on. The last term we end up with is a times rn. So if you look at this two summation, they are very similar, except the first term. The middle term, they share the middle term. AR here, a times r squared here, a times r squared, a times r cubed. Therefore, if we subtract one from the other, we are going to cancel almost all terms. That's what we are going to do. So if we subtract Sn from Sn, subtract r times Sn from Sn, what we are going to get is a minus a times r to the n. Very simple. Only the first term and the last term remain. And therefore, what is Sn? Sn is a times a minus a times r to the n divided by 1 minus r. Okay, so it seems we are done. Wait a second. Here is, we can do this only if 1 minus r is not 0. That means r is not 1. Okay, so we can do this only if r not equal to 1. So we have to be careful if this r is not equal to 1. What about r equals 1? R equals 1 turns out even easier because r equals 1 means Sn is a plus a plus a plus a plus a. Every term is just a itself. So it's an a if r equals 1. The special case of a equals 1, that means the initial term is 1, and the absolute value of r is less than 1 is you are going to have Sn equals 1 plus r squared plus r cubed plus r to the n minus 1. And it turned out that this one, because if you plug in a equals 1, you're going to have is just 1 minus r to the n divided by 1 minus r. This is a very useful formula. And for example, if n equals 2, you get 1 minus r squared divided by r is 1 plus r, which can be easily verified. And n equals 3, you get 1 minus r to the cube divided by r. What is r 1 minus r cube, which is 1 minus r times 1 plus r squared. So it's equals 1 plus r squared. That means that you can easily verify this for small values. And this summation just tell you this formula, this nice formula holds for every integer n. A very interesting case is when n goes to infinity. Whether you have an infinite sequence, and when the summation of 1 plus r squared plus r cubed, what are you going to get? You're going to get limit. So let's do this. Limit n goes to infinity. Sn equals limit n goes to infinity. 1 minus r to the n divided by 1 minus r. Because the absolute value of r is less than 1, so this term goes to 0. So what you're going to get is 1 over 1 minus r. It's a very nice formula. 1 over 1 minus r. So I hope you, this formula you definitely should memorize. 1 over 1 minus r equals 1 plus r squared. You have in this infinite. But the condition is the absolute value of r is less than 1. This is a very, very important formula.